Assalamualaikum. We are students from EKT318. Our mini project title is Bandpass Filter. My name is Rahman bin Abdullah. The content of our slideshow is the introduction, our aim and objective for this project, the methodology, and the result of our mini project. Introduction. Bandpass filter. A bandpass filter circuit or device is used to allow only a predefined set of frequencies to pass through it. It will filter all the frequency that is below the set value and above the set value. A bandpass filter can be obtained by cascading both high and low pass filter. Bandpass filters are largely used in wireless receiver and transmitter. Bandpass filters are used primarily in wireless transmitter and receivers. In a transmitter, it is used to limit the bandwidth of the output signal to the minimum necessary to convey data at the desired speed and in the desired form. In a receiver, a, a bandpass filter allows signal within a selected range of frequencies to be heard or decoded, while preventing signal at unwanted frequencies from getting through. A bandpass filter uh, a bandpass filter also optimizes the signal-to-noise ratio sensitivity of a receiver. Electrocardiogram (ECG or EKG). An electrocardiogram (EKG or ECG) is a test that measures the electrical activity of the heartbeat. With, with each beat, an electrical impulse or wave travels through the heart. ECG is composed of 5 waves, P, Q, R, S, and T. Signal could be measured by electrode from the human body in typical engagement. The signal from the electrode are brought to simple electrical circuits with amplifiers and analog digital converters (ADC).
Hello, my name is Badrul Amin Ahmat, and now I will discuss about our aim and objective for our project. Firstly, is to design a bandpass filter for heart monitoring system based on an ECG signal. Next, we will understand the mathematical equations based on bandpass filter. Next, we will determine the gain and phase margin of the system in a dot plot. And lastly, we will design a compensator for the phase margin of at least 30 degrees. For methodology, firstly we will obtain the dot plot, phase margin and gain margin of the system by using the Scilab. And the transfer function for the system is Gs equals to 5 times 10 power 4, which is 50,000, over S times S plus 10 times S plus 100. In order to design a compensator using phase-led network, we use these following steps. The first step is to determine the frequency for our new phase margin. Secondly, we will make this frequency our new gain crossover frequency, which is the omega c. Third, we will determine the value of alpha by using the reduction of gain formula 20 log alpha. Next, we will put the 0 z 1 decade below, and therefore we will obtain the z value, which is equal to omega c divided by 10. Next, we will find the tau from the z, where z equal to 1 over tau. And lastly, we will write the phase-led network transfer function as follows. GCS equal to 1 plus tau s over 1 plus alpha tau s. After obtaining the phase-led network transfer function, we will add it into the original system, which will result in obtaining the desired phase margin.
Hello, my name is Azizul Elmey bin Azizul El-Jeffry. In order to get the dot plot for the transfer function Ds equals 5 times 10 to the power 4 over S times S plus 10 times S plus 100, we enter the following commands into the Scilab. By using Scilab, we can obtain the phase margin and also the gain margin of the system. The phase margin of the system is 13.57 degrees and the gain margin of the system is 6.85 degrees. The bot plot of the system is obtained by using Scilab. For the compensator design part, we design the compensator by following the 6 steps mentioned in the methodology. Our desired frequency is 30 degrees and a 5 degree is added to allow a safety margin. The frequency for our new phase margin is at negative 180 degrees plus with 35 degrees, which equals to negative 145 degrees. Based on the bot plot, at negative 145 degrees, the new gain crossover frequency, omega c, is 1.802 Hz, which equals to 11.32 radian per second. The gain at omega c is 9.266 decibels. The value of alpha can be calculated by using the formula gain equals 20 log alpha. Solving for alpha will get alpha equal 2.906. Next, the value of z is calculated by using the formula z equal omega c over 10. Solving for z will get z equals 1.132. The value of tau is calculated by using z equals 1 over tau. Solving for tau will get tau equals 0.883. The last step for compensator design is rewriting the phase lag network transfer function as GCS equals 1 plus 0.883s over 1 plus 2566s. The transfer function in the red box is the product of DCS and GS. From the new transfer function, the phase margin is 31.17 degrees. This satisfies the requirement of the compensator design, which is the phase margin must at least be 30 degrees. Thank you.